Welcome to a tutorial on the FFT, specifically the FFT and gnuradio, and I'm going to take you through many steps of the FFT and show you what's underneath the hood of the FFT. First off, we're going to start off with the simple signal source, which is here a cosine wave. If you look at the sample rate, I've got it set up to 64 points. And I've got that intentionally set up to such a low number because we are going to go through the details of this, and seeing the details in a 64-point chunk will be a lot easier to see than seeing the detail in, say, a 512-point chunk or something larger than that. And you probably have already gathered that most of the time the FFT functions are done as a factor of 2, so 2, 4, 8, 16, 32, 64, and so on. So we're going to do our data collection in 64-point chunks. We got a throttle block here. If you haven't seen other tutorials on gnuradio, use the throttle block when you are just generating signals within the computer. In other words, if you have a microphone that's generating this signal, or if you have a signal that's going into a speaker. In other words, in both cases, a piece of hardware, you don't need the throttle block because the hardware will throttle the sample rate itself. But when you're just creating signals and displaying signals within the computer itself without external hardware, then you want the throttle block, because otherwise, so I've heard on the internet, the processor will tend to shovel the data out as fast as it possibly can and run your CPU usage all the way up to 100%. Some of the tutorials say to go ahead and put the throttle block equal to the sample rate. What I found is run the throttle block until you're happy with the response time you're getting out of the signal, out of your display. In other words, if you have a slider and you're trying to display data, and there's not a responsiveness to the slider, or there's a big lag in the slider, up the throttle rate, find a compromise between the CPU usage and the responsiveness of your data flow. And we have two QT GUI syncs, a frequency sync and a time sync. I'm using the QT version because, as I have heard in other tutorials online, very shortly, I'm at version 3.7 of gnuradio here. A lot of the tutorials are done at version 3.6, and they use the WX GUIs. But I guess the WX GUIs are going to be deprecated. I can't tell you all the details on why that is, but that's my understanding. So let's go ahead and start up our cosine wave. In order to do this tutorial, I've broken the cosine wave up into 64 discrete points. I'm deliberately showing this as points and not as a line continuum, because in reality that's the way it works. You get points going into an FFT. In our case, we're going to have a 64-point FFT, and so you have 64 input points, and the FFT is going to put out 64 output points. So the top screen, we're showing dots. The bottom screen, I like dots better, but I couldn't come up with a presentation on the bottom with dots. The reality is, on the bottom screen, I've got this configured for a 64-point FFT. There are 64 data points here. In reality, the way this is showing a point at a frequency of +1, a frequency of -1. The adjacent point here is at 0 and 0, so it's drawing the tent, but in reality you need to picture this as actually 64 discrete points. Now, what I really wanted to highlight is that when you see the FFT in gnuradio, what you are seeing is the power representation of the FFT. You're looking at the frequency content of the signal up here. The FFT is giving you the frequency content in this display. And you would think, well, that's what the FFT is supposed to do, give me the frequency content of the signal above. And that all sounds great, except for, quite frankly, that's not enough. The frequency content is a start, but the frequency content does not tell the whole story. Because when you have a real signal, you're going to have, in this case, this cosine wave could have been a sine wave, and I'm going to show you this in a minute. But frequency content, a frequency consists of a cosine portion of that frequency and a sine portion of that frequency. And the way GNU Radio gives you the QT data output, the way you visually see it is in this power presentation. So you're just seeing the frequency content, but you're not really seeing how much of that frequency content is cosine wave and how much is sine wave. However, when you're doing real DSP with IQ data streams, that which, knowing the frequency, knowing whether it's sine or cosine or how much sine or cosine is another way of saying the phase relationships of all of the signals, of all of the components, all the frequency components. You have to know the phase relationship of all those. And this display does not show all those phase relationships, and yet when you do a real FFT, that phase relationship is not lost in the real FFT. This presentation is extremely useful, but if you don't understand the subtleties of this phase relationship between the signals, then you're not really understanding the big picture, and you're not really ready for prime time for digital signal processing. And that's why I'm going to spend a lot of time here, and we're going to really break apart an FFT, not just on what you see on this screen, but really what is going on underneath the hood of an FFT. So let's go ahead and take this cosine function. I put a variable slider in here, and I also got a clicker here. And I'm going to click it up. And the first thing we're going to notice is I went to a frequency of 2 Hertz, and sure enough, the frequency went to a spike at 2 Hertz and minus 2 Hertz. I'm not going to get into negative frequency yet. Perhaps in a later tutorial I'll get into that. But, or maybe we'll touch on it a little bit later on into this tutorial. But you can see the frequency is at 2. Click it up. Now we're at 3, just as you'd expect, right? But you're going to see there's a lot more that's under the hood here. There's a lot more subtleties to this. And we're going to go over it in this tutorial right now. Now, one thing I want you to notice about this cosine source is I'm going up in frequency. You can see it's already starting to deviate a little bit from a cosine wave. That's almost a cosine wave, but it's not exactly a cosine wave, and I'm going to have to deal with that later on in this tutorial as well. Nevertheless, we're at a frequency of 4, a frequency of 5, a frequency of 6, and you can see these nice beautiful spikes moving along at a frequency of 6 and minus 6. And I say nice and beautiful because there's even more subtleties to this. What happens when you have a frequency of 5.5 Hertz or 6.25 Hertz? This beautiful picture below starts to degenerate very, very quickly, and we're going to see that in this tutorial, and that has to do with why you window. We're going to touch on why you window signals, and it's going to also touch into windowing and leakage. They're related in the sense that you window in order to address the problems of leakage. So you don't get leakage when your sample rate's, in our case, 64, and you lay a frequency perfectly, 1, 2, 3, just like this does, 4, all the way up to 64, you don't get leakage. And so that's another subtlety here. Unless it's in this GNU Radio, it's kind of hard. You have to go out of your way to set up an example where you see leakage. And I'm going to let you see leakage. And then we're going to explain it. You're going to see what it does to the FFT, and we're going to see why you want to window when you get leakage. So the other thing I wanted to point out is I didn't want to connect these dots. I wanted them to just be dots, because in reality, for a 64-point FFT, we have 64 discrete input points coming in. So if you were to look at that spread of dots, you wouldn't be able to tell me that that happens to be at 18 Hertz. when you do an FFT on those dots, it'll tell you, oh yeah, that's an 18 hertz signal. But you won't be able to see it here. And I didn't want to connect these dots because this starts to look like a scribble, and I would rather have you see the dots that you can't make out in your brain rather than having it be a scribble, because the scribble is actually more deceptive than the dots. The dots, there is 18 hertz there, perfect 18 hertz there with those dots, but if you saw the scribbles, you would see something that almost looks like 18 hertz, but it would look like scribbles, and then you would think, well, that's not a perfect 18 hertz, and it really is a perfect 18 hertz. If you want to experiment, you can try to connect the dots and see it for yourself. Anyways, the other thing I want to quickly touch on is, as you up the frequency, when you get to half the sample point, that's the 32 out of 64. Notice here, this would be 32 hertz across here, so we're getting we're hitting the top of the cosine wave and the bottom of the cosine wave, the top of the cosine wave, the bottom of the cosine wave, top, bottom, and I can tell you right now, this is very close to a cosine wave, but it's not exactly a cosine wave. If this were an exact cosine wave, those 32 dots would be exactly at 1, -1, 1, -1, 1, -1. So it's very close to a cosine wave when we take it up to 32 hertz, but not quite. Now, we're going to see with the sine wave, what would you get with the sine wave if you had 32 hertz? You'd start at 0, 0, 0, 0, and all you get is a straight line of zeros. So in other words, a 32 hertz sine wave is going to show all zeros, whereas a 32 cosine wave will show alternating ones and zeros, which kind of gets into one of the subtleties of the FFT, and that is when you hit the half sampling rate, you can actually extract the cosine component of the signal, but you can't extract the sine component. So that's and then after you hit the 32, or in our case the halfway point, it starts folding back in. Notice it ran out. Now we go up higher. We're at 35 hertz, and now the frequency content, because of aliasing, is going to start folding back in. And I don't want to spend a whole lot of time on that, but when we get up to 63, notice how when we're at 63 hertz, and again we have kind of lost our cosine look here, but at 63 hertz we're right back to 1 hertz in the FFT domain. So that again is folding, or if you want to call it aliasing, it's kind of the same thing. The 63 hertz signal aliases all the way back into a 1 hertz signal. I'm going to close this out. We're going to go to the next one. This is exactly the same representation we had before, except for now it's a sine wave instead of a cosine wave. And I'm going to go ahead and start it up. We're at 1 hertz. Sure enough, it's a sine wave. Now what I want to show you is look at this. This is the exact same representation as what we had for the cosine wave. And while it's good, we still have frequency content of 1 hertz. This is not good, because it is good, but it's not good. You got to understand, when you see an FFT and it's displayed in power, you are seeing the power of the frequency content, but when you do the power of the frequency content, you lose the phase information. So this representation is not showing you the phase information of the underlying signals here. And that's extremely important to know, and we're going to spend more and more time going over what the real output of the FFT is. I should say the complex. We're going to study in great detail the complex output of the FFT as we continue on in this tutorial. So now we're up to 1, 2 hertz, 3 hertz, 4 hertz, same thing. Frequency goes out, but can't tell you whether this representation is not going to tell you whether you have a sine wave or a cosine wave, and that is extremely important. We're going to take this just one last thing before we quit this screen and move on. 32, notice this is a little bit different. Now this is not exactly a sine wave. If this was a perfect sine wave at 32 hertz, we would have all zeros. The dots would just be 0, 0, 0, 0. So this is close to a sine wave, but it has a little bit of a cosine wave component in there. So if it was a sine wave, if you had a 32 hertz sine wave on here, the output of the FFT would be all zeros. All 64 points of the FFT would be 0. So anyways, we're going to go ahead and move on to the next screen. Alright, now we're going to use the same setup we had before, but the only difference is I'm going to get into fractional frequencies. We're going to see a couple things that happen. First off, we got 1 hertz. Everything looks the same. Everything looks fine below. Now I've got the slider set up so that instead of clicking every 1 hertz, I'm going to click every quarter hertz. And we notice two things. First thing is the top won't stabilize. I'm going to fix that here shortly. I'm going to go into how to fix that. Second thing is, look at what happened to the FFT below. All of a sudden, when I was sitting at 1 hertz, we had 2 beautiful spikes, which really was 2 discrete dots, one at 1 hertz, one at 1.5 hertz, or minus 1 hertz. We wish we had one at 1.5 hertz. I'm going to take this up to 1.5 hertz and look at how awful the FFT output looks when you get to a fractional frequency, because we have 64 points across the FFT. There's no point that says I've got a 1.5 hertz frequency. When you do the FFT, you're going to construct it with sine waves between 1 hertz, well, DC, you're going to have DC offset, 1 hertz all the way up to 32 hertz. You could say 64 hertz, but it really isn't 64. It's all the way up to the half sampling point. So you're going to be constructing the wave with a DC component, and then technically components all the way up to 31 hertz, sine and cosine components, and then actually at the half sampling point you'll just be able to extract the cosine component of the signal. So anyway, we're going to close this out, and what we're going to do is stabilize. We're going to stabilize that frequency by essentially setting this up by putting this keep M and N block. So I'm going to go to that window where I put it in, and essentially now when we're on quarter frequencies, the pattern will repeat itself every 256 pieces of data because I'm on the quarter frequency interval. And so what I've done now is I'm going to keep 64 of 256. So I'm going to go look at every 256 chunks of data, and I'm going to just keep the first 64. And what that's going to do is that's going to stabilize the pattern on the screen. So let's go ahead and run that after I put the keep M and N in. And now I can put fractional frequencies up, and when I do that, it stabilizes here. Now this is where we're going to start getting into windows, because right now we've got the Blackman-Harris window. The rectangular window is essentially the no window. And notice if you did a Blackman-Harris, when you have a perfect 2 hertz, what would you rather have, the Blackman-Harris or the rectangular window? Well, you'd look at it and say, well, dang, it's obvious. Why are you even putting a window on there? Because the rectangular window looks very good to me, thank you very much. But the fact of the matter is, when you have a perfect frequency, you don't need a window. But the fact is, you never get in real signals, you never really get a perfect frequency. So what you really wind up with is some kind of a fractional frequency. Now look at what happens at 2 1/4 hertz. And the problem is, I'm not going to go into great depth on this, but the problem is, look at the FFT is going to take 64 points of data in, and it's going to process it. And the real problem is, I'm just going to tell you this, but I'm not going to go into the exact explanation here. But look at where the starting point is, look at where the ending point is, the ending point and the starting point don't match up, and as a result, in order to, essentially what happens is the FFT has to make a repetitive waveform that looks exactly like this. So it's going to take this waveform, it's going to stop there, then it's going to have a huge discontinuity all the way back up to the top again, and then build a repetitive waveform. So the discrete Fourier transform really is trying to construct this waveform repeating itself over and over again. Sort of like a Fourier series. With a Fourier series, you come up with what one period of the waveform looks like, and then you build a repetitive waveform. The DFT or the FFT is doing the same thing. It really has to construct this waveform repeating itself over and over and over again. So then when you get the tail end not matching the front end, you have a little bit of a problem that causes what they call leakage. And the problem with the leakage is, in order to truly build this repetitive waveform where it has the step in it, it has to use all the frequencies available to it to build that step. So as a result, now the output of the FFT looks very crummy. This is 2.25, even worse when we go to 2.5. Now look at that, it's really not looking that red hot, and this is where you start applying windows. Here's the Blackman-Harris window. Again, you might look at that and say, well, that still doesn't look that hot, but what it does do is, if you notice, we're on a scale that is down at 80 dB all the way down here. It really suppresses the outside energy on the outside frequencies. So there's a Blackman-Harris, there's a Hahn window. You know, different windows have different purposes. The Hanning window, Kaiser, and the rectangular is essentially no window. So this is this fractional frequency. Again, we're not getting in a whole lot of detail of the FFT yet, but I want you to understand why you use a window. And it's hard, it's a little bit subtle to see why you have to use a window until you force yourself into these half or fractional frequencies. So there's 3 Hertz, and again, being back to 3 Hertz, and geez, you'd say this looks perfect. And why would you apply a window? Because when I apply the Blackman window there, you say, well, that doesn't look so hot. But now let's go up to 11.5. So there's an 11.5, and notice we'll go up to the positive frequency because we won't talk about negative frequency yet. So here's 11.5, right about there. And now the FFTs can tell you that by 14 Hertz we're about 50 or 60 dB down. So it's pretty much suppressed all of that I'm losing my word here, the energy, the outside energy, the leakage energy. It took me a minute I had to actually pause the recording because the leakage energy escaped me. So what the window does is it takes all that outside leakage and it squishes it back into where the actual frequency content is. It does widen it out a little bit, but it does contain it much closer around the actual frequencies. So there, let's go back to the rectangular window and now look at 11.5 Hertz with a rectangular window. I mean, there's all the way from 19 Hertz all the way to from 0 to 19 Hertz. It never gets better than 30 dB. Well, I don't know, maybe 30 something dB. The bottom line is that's terrible. And that's why instead of a rectangular window, you apply a window like the Blackman window. You can learn more about why you pick a window, but the important thing is you'll want a window. So we're going to go ahead and stop this particular one here, trying to give you a little bit of an introduction as to why you want a window. Alright, now we're going to get into the meat and potatoes of this. We're going to, instead of using the GUI interfaces from gnuradio. We're going to go over to the Fourier analysis box and pick an FFT, and we're going to bring it over into our window here. And when we open it up, we're going to have an input type of a float. The output's always going to be real on an FFT, and we're going to see that. In this case, we're going to use the forward FFT. No, we're not doing an inverse FFT. By forward, it means we're translating a time domain into a frequency domain. The reverse is translating a frequency domain into a time domain signal, or back into the time domain, I guess. In order to properly use the FFT block, as I understand it, you have to convert the stream of data into vectors. So we're going to use this stream to vector data. The vector length, I had a little bit of confusion about this, is 1, and the number of items is 64. And I'm trying to figure out where that 64 comes from, but don't put down 64 as the vector length. I think I did that originally and wound up getting very messed up. Took me a while to figure that out. We're going to first off is we're going to go ahead and I'm going to disable this and this, which is the GUI time sinks. Now, the GUI time sinks, I'm not really using those for time sinks. I'm going to be using those for frequency sinks. I'll explain that to you in a minute. But if I'm going to do this, then I need to have a QT, just a, I want a null sync. Let's see if I can find a null sync up here. There we go. So we're going to have a couple of null sinks I'm going to put in here, because sometimes the GUIs take up so much of the screen that I can't show you what I want to show you. So I'm going to put 2 null sinks in there, and right now I've got a real number coming out going into a complex, so I got to change that to a float input. That'll be okay. Change that to a float input. Okay, so now what we're going to do is just focus on what is coming out of the signal source. And sure enough, we got a sine wave. And I'm changing the frequency, and again, I like dots better here, and let me go back out here. My variable range, I really should do I've got it starting at 0 and stopping at 100. Let's just try 63 for now, even though that's probably too much. So we're starting at 0, stopping at 63, and this is why I had dots before, because this is a really crappy representation of what's going on here. I like the dots better. Anyway, so we got a signal source as a cosine. Got the throttle rate at 64K. Now I got this delay block in here. This is another thing that because I'm not getting a cosine. When I'm going to really show you what's under the hood of a FFT, we got to really line that thing up so that we can have either a sine wave or a cosine wave. So I'm going to put this delay block in, which allows us to delay the stream by a certain amount, which I've got a variable here, right here, a variable delay, and I can vary that between 1 and 64. And that's going to allow us to that's going to allow me, let's go ahead and look at this again. That delay line is here, and now what that allows me to do is shift the signal anywhere between a sine wave and a cosine wave. So that comes up as a cosine wave. But remember, before when we moved the frequency, and again, I like the dots better. I don't have the dots here, but I think the dots are better. But now I can actually readjust that, and make it a sine wave or a cosine wave. And in reality, I'm not going to be varying too much off of 1 hertz, but see, there's a higher frequency, and I can change the phase. Now, if you want to use that delay block, what I have is a QT range, which I'm using for the variable slider. And when you're using the QT GUIs, to get the slider, you want to use GUI range. In the old WX GUI, they have a slider, but in the QT, it's to get the slider, you want the range. So I'm doing 1 hertz steps. We're starting at 0 to 63. I'm going to go ahead and put the default value on the delay at 0. And actually, we can change this from a slider. We'll do a slider, or you can do a slider and a counter. Actually, I like, for the frequency, we'll go ahead and change this to a slider and a counter so we can see what our frequency actually is. So bottom line is, we got a cosine wave. Now I've got this delay block in here that I can vary it anywhere between a cosine and a sine and anything in between. 2 sliders, 1 slider for the GUI, or for the frequency, and the other slider for the delay. And let's, again, starting here on the GUI time sync, we'll open that up. So that's what we've got right now. Just to reiterate, there's the frequency. So we got a frequency of 4, and we can delay, because we want to really look at what's going into that FFT. We want to be able to change the frequency, and we want to be able to change the phase. So now, the other thing about the FFT, this is the FFT we really want to look at. That's what gnuradio actually uses. We're trying to get away from the GUI FFT and look at what really comes out of an FFT, so you can see what's under the hood of an FFT. In order for this, the FFT function in gnuradio needs vectors. So you got to take the stream of data and convert it to vectors. Again, the important thing is, don't make that 64, because that's what I thought it wanted. It doesn't want that. I'm not sure where the number of items comes from. I don't know. The number of items is a sample rate. So yeah, the number of items is 64. The vector length is 1. Don't put 64 in the vector length. It won't work. Alright, so now we're stuffing the FFT with 64 points. And what comes out of the FFT? Let's talk about that for a minute. What actually comes out of the FFT are 64. You put 64 real points in, although we're going to learn later when we do complex numbers that in real DSP, or more complicated DSP, I should say, you're going to stuff the FFT with IQ data, and IQ data would be 64 complex points. The I would be the in phase, which, the I is not the imaginary part of the data. The I is the in phase, which is actually the real data, and the Q is the quadrature phase, which is actually the imaginary data. So the I is in phase, Q is quadrature. So you're actually going to have complex data going in, which is still would be 64 data points, because that's what I want to work in to illustrate this, is 64 point FFTs. And here's our FFT. The FFT size is going to be our sample rate, which is 64. I think I'd already explained before. We're doing a forward FFT. And what's going to come out are complex numbers. So you put 64. You put 64 points in, it processes that chunk of 64 points, and it gives you 64 points in the frequency domain. Those 64 points are actually going to be complex numbers. And these two things. We're going to strip off the imaginary part of the complex number and the real part of the complex number. And now I'm going to use time sinks because I don't know how else to do this, but I really want you to see what's under the hood of the FFT. So we're going to use time sinks, but now we're actually in the we've got the output of the FFT. So these really aren't going to represent time sinks. They're really going to represent frequency points. We're going to get 64 points on here, and those 64 points, I'm going to get the null sinks out, and I'm going to disable the sinusoid. By disabling it, I don't want that to come up anymore. So we've got a frequency coming in. It's in 64-point chunks. We're going to do a 64-point FFT. The output of the FFT is going to be complex data. We're going to sort the complex data into the imaginary part and into the real part. And then we're going to look at this on time sinks, but they're not time sinks. It's just these are convenient things, convenient items to look at the output, look at the two outputs on the FFT. So let's go ahead and start her up. And I got this set up to points. So now what we're looking at is the output of the FFT when we have a cosine wave coming in. And when we have a cosine wave coming in, I just happen to remember that. The problem with these gnuradio GUIs, especially the QT ones, I haven't been able to figure out how to crunch these down. I wish I could crunch these way down and make these half the size so I could get 3 pictures on here at once. And I can't seem to do that. So we can look at the two frequency outputs. I shouldn't say that. We can look at the imaginary part of the FFT and the real part of the FFT and take it from there. I don't know what I just did there, so I'm going to reopen it again. There we go. Okay, so starting with the cosine wave, we're going to start adjusting the frequency. And what you're going to notice is what really comes out of an FFT is a real component and an imaginary component. And again, we're not going to have any, because I got this thing on perfect frequency increments, I don't have any half frequencies. I don't have 10.5 or 11.5. So we're not going to get any leakage. I think I've got my next one after this is going to start showing leakage, and then you're going to see what's going on even more so. But I don't have any leakage going on because I don't want you to see the leakage just yet. So here, what is really under the hood of the FFT, you're going to have the real part of the output of the FFT, which is, again, in this case, we have we know we have a cosine wave. It's not really a cosine wave. I'm going to show you how to make it a cosine wave. I'll get it as close to a cosine wave as I possibly can. There. That's as close as I can get to a cosine wave. So I changed the delay, and basically what happens, remember this slider is going to change the delay. But what happens is this represents how much cosine component is in the signal, and this is representing how much sine component is in the signal. So the imaginary part of the output of the FFT is the, if you will, the sinusoidal, not the sinusoidal, the sine wave component. The real part is the cosine component. And so I can vary the frequency. Notice when I vary the frequency, we'll go all the way back to 1. And we'll put the delay I'm going to change the delay till I get something that I like, which I don't like that. There. There's our delay. Frequency is 1. Look what's coming out of the imaginary part of the FFT. Nothing. Because this is a pure cosine wave going into the FFT. Look what's coming out. We've got a component at 1 and we got a component at 63. So the very last point is a 1 and not 0. 0 actually represents DC. So we got the number 1 point and number 63 point. And this brings up yet another thing about what you're seeing when gnuradio gives you the output of an FFT and converts it to log magnitude. They actually, remember the GUI output is going to take, at 1 hertz, it puts the 2 spikes right in the middle but just barely separated from each other. So in gnuradio, when they represent the FFT, they're actually folding these two guys back in on the center. But mathematically, and realistically, when you do an FFT for real, mathematically, the FFT goes from 0 to 63, so that's 64 points, because I have a 64-point FFT. If it was a 512-point FFT, it would go from 0 to 511. But so, and what you get is component 1 and component 63 mirror each other, which it's kind of bizarre how that works. Component 0 stands alone. If you go to 0, that's the DC component, and we can't really see it all. It's down below, but that I think should probably be 0. I don't know why that looks like that. Don't focus on that too much, because something isn't, don't think about that, because I would think that should have been well, no, if I went back and looked at that 64 point, there would be some DC offset to that. Maybe we can go back and look at that, but so anyways, I know I'm kind of blabbering here, but this is extraordinarily important to understand. I'm going to try to let you see the whole window. There we go. That, again, we're putting a real data stream in, we're getting a complex data stream out. Because the real data stream is going to have sine wave and cosine waves embedded in there. This is still not even talking about a complex data stream in, which is getting into IQ data processing. We're not even to IQ data processing yet. This is just turning a real waveform, looking at the frequency content of a real waveform. But the frequency content is going to contain sine and cosine components. So we vary the phase. I can tell you right now that really is going to be like a negative cosine wave. If I looked at the frequency component of that, it's going to be a negative cosine wave at 1 hertz. And if we change the phase, notice the cosines are always the same direction. So when that's going to be a negative cosine wave. There we go. That's perfect negative cosine wave with no sine wave in it. In other words, that would be a negative cosine wave with no phase shift. This would be something in between, because it's got sine wave and cosine wave. Notice the sine waves are always opposite direction. The cosine waves are always the same direction. So if we went back, I'm going to take it all the way to here. That's going to be, I'm going to keep going one more right there. That's a positive sine wave. The positive sine wave has the plus and the plus up at the high end, negative at the low end, and notice we have no cosine component. I'm going to take the delay back. We're going to zero out the imaginary part of the FFT. Now we have 2 positives. That's going to be a perfect positive cosine wave. Take it back some more. Now we got a negative sine wave when I zero out the cosine component. There's a perfect negative cosine or negative sine wave. Keep going back, and there's a perfect, right there, almost perfect negative cosine wave. So the point is, what gnuradio does, when it takes the output of the FFT here, takes all these points, it takes the log magnitude. In other words, it takes the amplitude of this guy and the amplitude of this guy, squares them, well, squares this guy, squares that guy, adds them together, square roots them, and that then gives you the amplitude or the magnitude. And then on top of that, what gnuradio does is it refolds these FFT outputs back. It makes the folding point around the center instead of around the ends. So that's what's underneath the hood of the FFT. So you might want to play around with this yourself, because this is what the real output of an FFT looks like. Now we're going to go to the next section, and this is where it gets kind of fun, because now we're going to do the same thing we did before. So now here I'm going to use the GUI time sync, and again I'm going to use the FFT, and we're going to put a time sync on there, and we're going to see the real and imaginary parts, because now it's not really in time domain, it's the frequency domain. But now we're going to have fractional frequencies. And now what we've done is I've superimposed the real and imaginary points of the output of the FFT onto the same screen. So we've got the imaginary is red and the real is blue. And that's the output of the FFT. This is the complex data stream out of the output of the FFT. And now I like this representation better, but I didn't want to start off the bat putting the imaginary and complex on the same screen. I wanted you to see them separately. Now I'm going to combine those two together. Now we can have changed the delay. See how the delay is changing? Now let's go through this. And oh, I thought I had fractional frequencies. I'm sorry, I don't have fractional frequencies. I think I have them next. So the bottom line, the purpose of this is to show you we got 64 points coming in to the FFT, and these are 64 real points, and the output of the FFT is 64 complex points. So each point has a real part and an imaginary part, real part, imaginary part, real part, imaginary part. So this shows you the structure. So this really is not any different than what we had before. It's just a little different representation, where instead of let's go back to this, instead of doing the breaking it into two channels, one for the imaginary part and one for the real part, I went ahead and used the GUI time sync and let that do the processing for us. Now we're going to do the same thing, but this time going back to one of the earlier screens, I'm going to use the keep M in N. So now we're going to be able to change the delay and have fractional frequencies. So this is now where the rubber is going to start to kind of hit the road. So everything looks the same here. Now we've got a fractional frequency. Notice the starting point and the end point are not lining up, and what is happening is we're getting leakage. Now that energy, we're at 2 1/4, that energy, we don't get nice point there, nice point there. Now it starts to kind of build. I'm going to go to 2.5. So there's 2.5 hertz. And while see this is not in the logarithmic domain. This is just in the linear range. So this may not look that bad, you know, this, but that is like 20 dB down. And this might be, based on what we saw earlier, like 30 dB down. So when you convert this to the magnitude or decibels, this energy leaks all across the whole spectrum, which is not a good thing. But let's go ahead and let's go to we'll go to 3 1/4. And with 3 1/4, it starts off as a cosine wave and it kind of ends at a sine wave. And so the FFT kind of has to interpret what's going on at 3 1/4, and so it gives you different points, as you might expect. If you took it down to say 1.5, If you go to 1.5, you're going to have energy, more or less, a fair amount of energy at 1 and some energy at 2. And then you're going to have a whole bunch of leakage in between. And if we change the phase, we can start rotating the phase. And you can see the cosine. I mean, look at that. I mean, it's just rippling and wobbling all over the place. That's because of this huge discontinuity, which, by the way, that discontinuity is, it really is the same whether we're doing the FFT here or whether we're doing it here. The FFT has to deal with that discontinuity, whether it's in the middle or whether it's there and there. Because what the FFT is doing is, again, going back to Fourier series, if you do a Fourier series, the Fourier series tries to replicate a repetitive waveform. The discrete Fourier transform is doing the same thing. It's trying to replicate. It takes this chunk of data, it grabs the 64 points, and then it says, how can I build a set of frequency components such that I replicate this over and over and over again. You don't have to totally understand what I mean by saying that, but that's kind of one of the subtleties, and that's why you get a discontinuity in the FFT, because it really is making a repetitive waveform that goes like this, then up with a big discontinuity, and then repeat itself again and again and again. It's trying to replicate that repetitive waveform with the frequency content as described by these 64, well, it's not really 64 frequencies. It really is, you get 31 frequencies and a DC component. You get 31 frequencies, a DC component, and then at the Nyquist sampling rate you get the cosine component. And let me show you that. That might be actually kind of interesting. Let's go up to 32. I don't know why. Well, that was the delay. I gotta take the frequency up. Let's take it up to 32. And I'm going to show you something. You don't have to, just for reference, you don't have to think about it too much. But there's no matched pair for the center guy. And as I change the delay, if we make this a, crap, I really can't do it. My delay's not set up right. If I had a finer resolution on the delay, which I don't, if I could turn that into a sine wave, this would all zero out. Well, the bottom line is, when you're on the 32nd, when you're in the center point, we're on the center point of the FFT, you only can get a real component out. You can't, imaginary parts can only, remember complex conjugates? You probably heard that. You only get complex numbers when they come in pairs, and you never can have a complex number, at least in the DSP realm, without having its complex conjugate pair. So when we're in the center, if you had a center imaginary number, there's nowhere for the complex conjugate to go. So you can never have an imaginary point on the exact center frequency. You can have a real part, but you can't have an imaginary part. And again, what that kind of means is that if you had a frequency component right at the half sampling point, you can capture the cosine content of that, but you cannot capture the sine content of what's at that frequency. And that's why the sampling rate is broken. Sampling rate over 2, it's actually broken, even though you can get the cosine but not the sine. So that's some more food for thought. Alright, now lastly, what we're going to do is look at the FFT with an incoming signal, which can be on a fractional frequency, and it can have a delay, so we can go between sines and cosines. And we are going to use the gnuradio time sync, because that really is showing the frequency content, because this FFT is the real deal. That's that's really generating the real kind of stuff that would come out in your signal processing, and this is just what a convenient thing to use on the screen. So I'm in the frequency domain here, so the time sync is going to be putting out frequency content, and I know I've explained that before. One other thing that I may not have explained is that if you do use the delay function, I may have not explained this before, but if you use the delay function and you want a delay variable like this, you have to convert the delay item. The delay variable has to be converted to an integer. So you make a variable delay, you want to run the delay block with that delay variable. However, the delay block is only, you're getting chunks of data, and you're delaying the data by a number. Like I'm delaying it 1 by 1. I'm delaying it by 1 sample or 2 samples or 3 samples. So the delay function can only take an integer input. And so the bottom line is, if you want to use the delay function here, you've got to, this whole gnuradio companion is it is building Python scripts to feed into the gnuradio system. So while with gnuradio you don't have to know Python, there are times where if you want to do special things, you got to kind of understand it's doing Python. So in this case, we're taking the variable delay and we're going to convert it to an integer by saying int brackets delay, and that'll make the delay box work. If you don't do that, the delay box will not work, because the delay has to have an integer. Okay, so that's only if you want to construct this for yourself. Remember to alter the input to the delay and make it an integer. Alright, so let's open it up, and this is our last panel for this tutorial. So now I'm not going to show you the sinusoidal wave. I hope by now you kind of got an idea what that looks like. I can vary the frequency. I'm varying the phase, and I can vary the frequency. And now we're going to use the ability to change the window. So let's go to the rectangular window, and again, because we got a nice, beautiful, perfect frequency that is exactly 2, we get 2 nice spikes when we use the rectangular window. But if we use the Blackman-Harris, you might say, "Ah, God, that looks pretty bad." But you're never really going to have beautiful sine waves and cosine waves with no discontinuities that are perfect repetitive pattern to the sample period that you take. So let's take our fractional frequency. We're going to take that up to 2.5. Let's take it up. Take it up to 7.5. There's 7.5. There's the linear output of the FFT. This would really be 64 points, but this particular GUI doesn't let me put it in points. The time GUI does. This is the time one, even though that's frequency. So the time lets me put the discrete dots, which I like way better for illustration purposes. But this really represents 64 points, and they just kind of connect them together. There's the rectangular window where it's 7.5 Hertz. Now what do you like better, that or that? There's the Kaiser window, there's the Blackman window. Each window, it's all a compromise on how much spillage do we allow out here and how fat is it here. So the deeper it goes here, the fatter it gets here. If you don't want it, if you use a rectangular window, the rectangular window is, if you wanted to know, all you want to know is the closest estimate to the frequency and nothing else. The rectangular window is still going to give you the tightest ability to predict the frequency, but it's smearing everything else. Now, if you wanted to say, when you're doing dynamic range stuff, and you want to know, okay, how much content really how much content is there really out here? If you apply a different window, you can say, well, given that signal, I might not be able to tell you exactly where it is in here, but I can tell you it's not out here. So the windows really is how you want to play with your dynamic range of the signal. So when you apply windows, and again it's for these half frequencies or partial frequencies, it makes a trade-off between dynamic range outside of the frequency of interest and how well can you predict around the frequency of interest, and then how much can you say with confidence there's no crap out here. And you pick the window depending on what trade-off you want. There's the Blackman, the hand window. The hand window, as you can see, it's a little pointier, but it's got more leakage, allows more leakage through. The Hamming window doesn't even hardly look like much of a window, but again, it's going to pull some of the leakage down. Let's look at that compared to the rectangular. I don't see any. I'm not quite sure what's going on there. And this doesn't look like the Hamming window is really doing anything. So there's the rectangular window. We'll go to the hand window, and you can see it's helping the leakage. But if you really want to knock the leakage down, there's the Blackman-Harris. You pick the window. It's all compromised. But the other thing is, remember again, mathematically the DFT is done from 0 to 63, and you're going to get this kind of symmetry, and the GNU radio is going to take this content, fold it back in around the center. So this actually is going to come here, and that comes here. So they, rather than folding around the ends, they fold around the center, and then it's taking the logarithmic amplitude of this to get this. Now, the window, the other thing is, when you do an FFT with a window function, let me go back here. Let me close this out, and this is going to end the tutorial. When you window a function, now in this case they're windowing the function here. I'm sorry. I'm actually, when I'm showing you the windowed function, I'm actually showing you this window down here is in this GUI sync. That is being generated by this QT GUI sync. This time sync, which is because I'm in the output of the FFT, is not really the time sync. It's looking at the time points here and in the complex domain. So that is the that particular GUI window. But getting back to what I was trying to say, when you window an FFT, the window function, and I'm not going to get into this right now, but you take the 64 points that go into the FFT and you apply the window right there. You take the 64 points and you apply the window function, then you put those modified 65 points into the FFT. So you do the windowing before the FFT, not after the FFT. And with that, I think I'm going to conclude this tutorial. Thank you for listening.